Have you ever witnessed the gigantic scale at which bread, sandwiches, and bagels get made in factories? These essential foods might seem simple, but require an insane amount of automated machinery to match the output of millions of products per day. Today, we'll follow the impressive journey from raw grains to finished bread, showing you a process you've never witnessed before. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry where every gram of input is measured, every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proof of climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edged slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft-tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms, equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement, so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, a mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow-wrapped sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity, develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, The seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of two steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees C and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. High-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 gralus of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within +/- 1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing, allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Cs to 98 degrees Cs. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick and place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings such as extra chocolate chips, coarse sugar, or sea salt can be added before baking. These are applied using vibratory feeders or pneumatic dispensers synchronized with the conveyor speed. Toppings are placed with positional accuracy controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. Water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees quarks. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. A high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. Heat-sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, Cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate in robing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. The process for Haribo gummy bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree Kelvin. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, the hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Celsius and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar-glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees Celsius. To create multiple flavor variants, the unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees, with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. Polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the weigh-filler interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle, verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk: sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees C. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece-counting systems for final packaging. For bagged formats, vertical form-fill seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, Mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. from sugar loading to pallet stacking. Each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are mated using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing Nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored Nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. A fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, the spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the Nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 degrees Celsius to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans, but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills 2 parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of 2 flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or preformed containers, sealed, and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line. Spaghetti production in factories begins with the precise blending of durum wheat, semolina, and water in massive stainless steel mixers that rotate at controlled speeds to ensure uniform hydration. The semolina used is specially milled to have a coarse texture that provides the ideal structure for pasta, unlike finer flours used in bread or cakes. Water is added in exact ratios, typically around 30 to 33% by weight, to activate the gluten without making the dough too sticky or too dry. The mixing process takes approximately 15 to 20 minutes, during which sensors monitor temperature and moisture levels to prevent overheating or uneven consistency. Once the dough reaches the right consistency, it is fed into a vacuum deaerator that removes trapped air bubbles, preventing imperfections during extrusion. This vacuum step is critical because air pockets can cause the spaghetti to break or cook unevenly later in the process. The dough then enters a twin screw extruder, where hydraulic pressure forces it through bronze or Teflon dies with hundreds of tiny holes arranged in precise circular patterns. Bronze dies are preferred for traditional pasta because they create a slightly rough surface that holds sauce better, even though they wear down faster than Teflon. Each die is engineered to produce strands exactly 2 millimeters in diameter, with tolerances of less than 0.05 millimeters to maintain consistency across entire production runs. As the dough is extruded, it emerges as continuous strands that are immediately cut into standardized lengths of 25 to 30 centimeters using high-speed rotating blades. The cut strands are gently guided onto moving conveyor belts made of food-grade polymer that prevent sticking while allowing airflow underneath. These belts carry the spaghetti into the first drying chamber, where temperature is held at 35 degrees Celsius, and humidity is kept below 60% to begin slow moisture removal. Drying is not a single-step process. It occurs over 4 to 6 hours across multiple zones, with gradually decreasing humidity and increasing temperature. In the initial drying zone, moisture is slowly drawn from the outer surface of the strands to prevent cracking or surface hardening. The second zone raises the temperature to 45 degrees Celsius while reducing relative humidity to 40%, allowing moisture to migrate from the core outward. In the third zone, the temperature climbs to 55 degrees Celsius and humidity drops to 30%, accelerating the drying of the pasta's interior without collapsing its structure. A final conditioning zone at 30 degrees Celsius and 55% humidity allows the pasta to equilibrate, ensuring even moisture distribution throughout each strand. Throughout the entire drying process, robotic arms with infrared sensors continuously scan each batch for cracks, warping, or discoloration, automatically diverting defective strands. After drying, the spaghetti is cooled in a controlled environment to room temperature over the course of 90 minutes to prevent condensation and microbial growth. Cooling is done with filtered, dehumidified air to avoid reintroducing moisture that could lead to spoilage during packaging. Once cooled, the strands are gently shaken and separated by vibrating screens that disentangle any strands that may have adhered during drying. A powerful airstream then blows away any residual semolina dust or small fragments that could affect texture or shelf life. The spaghetti is then fed into precision weighing systems that portion out exact quantities, typically 500 grams or 1 pound, into food-grade polypropylene bags. Each bag is sealed with heat, creating an airtight barrier that protects against oxygen, moisture, and pests for up to 2 years. Inside the sealed bag, A small oxygen absorber packet is often included to further extend shelf life by eliminating residual oxygen. Before sealing, a metal detector scans each package to ensure no foreign materials, such as metal fragments from machinery, have contaminated the product. The packaged spaghetti is then labeled with batch numbers, expiration dates, and nutritional information using high-resolution inkjet printers that operate at speeds exceeding 100 packages per minute. Each label is scanned and logged into a centralized digital tracking system that links every box to its exact production time, raw material source, and quality control checkpoints. The boxes are stacked by robotic arms onto pallets, wrapped in stretch film, and moved via automated guided vehicles to a climate-controlled warehouse. The warehouse maintains a constant temperature of 18 degrees Celsius and humidity below 50% to preserve the pasta's texture and prevent mold. Before shipment, random samples are pulled from each batch and sent to an on-site laboratory for microbiological testing, including checks for salmonella, E. coli, and mold spores. The lab also performs texture analysis using a texture analyzer that measures the firmness of cooked spaghetti to ensure it meets the industry standard al dente criteria. Each batch is tested for cooking time, with the target being 8 to 10 minutes in boiling water, and deviations trigger an automatic review of the drying parameters. Once cleared, pallets are loaded onto refrigerated trucks that maintain a steady 10 to 15 degrees Celsius during transit to prevent thermal degradation. The entire production line operates 24 hours a day, 7 days a week, with only brief scheduled maintenance windows to clean and inspect critical components. Every hour, the extruder dies are manually inspected and cleaned with high-pressure steam to prevent bacterial buildup in the microscopic holes. The mixing tanks are sanitized with food-grade citric acid solutions after every batch to eliminate cross-contamination risks between different pasta shapes. Workers in the facility wear full hairnets, gloves, and shoe covers, and all entry points have air showers that blow away dust and particles before entry. The factory's HVAC system filters air 15 times per hour, maintaining a Class 8 clean room environment to meet international food safety standards. All equipment is designed with smooth, seamless surfaces and no crevices where dough or debris could accumulate and become a breeding ground for microbes. Robotic vision systems monitor the color and shape of every strand exiting the extruder, rejecting any that deviate from the established visual profile. If a strand is found to be too thick, too thin, or irregularly shaped, the system automatically adjusts the extrusion pressure in real time to correct the issue. The factory produces over 12 million kilograms of spaghetti annually, enough to feed approximately 200 million servings per year. Each kilogram of finished spaghetti requires precisely 1.1 kilograms of semolina, with the remaining 0.1 kilogram lost to moisture evaporation during drying. The water used in production is filtered through reverse osmosis systems to remove minerals that could affect dough texture or flavor. Wastewater from cleaning is treated in an on-site biological filtration plant before being safely discharged into municipal systems. Used semolina dust is collected and sold to livestock feed manufacturers, reducing waste and contributing to a circular economy model. The energy used in drying is partially recovered through heat exchangers that capture exhaust heat and reuse it to preheat incoming air. The factory's lighting system uses motion-activated LED panels that dim or turn off in unoccupied zones to reduce electricity consumption. Every machine on the line is connected to a central AI monitoring system that predicts maintenance needs based on vibration patterns and motor load. This predictive maintenance reduces unplanned downtime by over 40% compared to traditional scheduled servicing. The factory's quality control team includes food scientists with PhDs who regularly test new semolina varieties and drying algorithms to improve efficiency. New production runs are always preceded by a trial batch that undergoes sensory evaluation by trained tasters who assess texture, aroma, and mouthfeel. Each factory worker undergoes quarterly food safety certification and participates in simulated contamination drills to maintain readiness. The entire process, from raw semolina to sealed box takes less than 7 hours from start to finish, making it one of the most efficient food manufacturing systems in the world. No preservatives are added to the spaghetti, relying entirely on low moisture content and airtight packaging for long-term stability. The final product contains no cholesterol, no saturated fat, and no added sugar, making it a nutritionally neutral staple in global diets. Every strand of spaghetti produced in this facility is identical in diameter, length, density, and cooking behavior to the one before it, thanks to relentless automation and real-time feedback systems. The factory operates with zero tolerance for human error in the final packaging stage, as even a single mislabeled box could trigger a nationwide recall. Lasagna production in factories starts with a dense, coarse semolina flour blended with chilled, purified water in a slow-turning horizontal mixer that prevents overdevelopment of gluten. Unlike spaghetti dough, lasagna dough is formulated to be slightly drier and more rigid, enabling it to hold its shape during stacking and baking without becoming soggy. The water used is pre-cooled to 12 degrees Celsius to maintain dough temperature below 24 degrees during mixing, preserving the natural starch gelatinization profile. After blending, the dough is rested for 15 minutes in a sealed, humidity-controlled chamber to allow gluten strands to relax and absorb moisture evenly. This resting phase is critical. It reduces the risk of sheet cracking during the subsequent rolling process by allowing internal tension to dissipate. The dough is then fed into a tandem roller system composed of hardened steel cylinders that compress the dough in 7 incremental passes, each reducing thickness by only 0.08 millimeters. The final roller gap is set to 0.62 millimeters, producing sheets so uniform that laser sensors can detect deviations as small as 0.01 millimeters across the entire width. As the sheets emerge, they are immediately swept by a gentle stream of dry, filtered air to prevent adhesion to the metal conveyors and to initiate surface drying. The sheets are not cut immediately. Instead, they travel continuously along a 30-meter long drying track suspended above a series of radiant infrared heaters. These heaters emit targeted wavelengths that dry the top and bottom surfaces at different rates, minimizing curling and warping caused by uneven moisture loss. Humidity sensors embedded in the drying tunnel adjust airflow in real time, maintaining a gradient that pulls moisture from the core outward without forming a hard outer shell. Every 12 seconds, a robotic arm lifts a section of the continuous sheet and tests its tensile strength by gently stretching it between calibrated claws. If the sheet fractures or elongates beyond 12% of its original length, the system flags the batch and adjusts the next dough batch's hydration level automatically. Once dried to a moisture content of under 10%, the sheets are cooled in a tunnel filled with recirculated, sterile air to prevent reabsorption of ambient moisture. At this stage, the lasagna sheets are still flexible enough to be handled without breaking, but too brittle to be rolled back into dough. A high-speed cutting station then slices the continuous ribbon into individual rectangles using tungsten carbide blades that operate at 1,200 cuts per minute with zero blade wear. Each piece is precisely 10.2 centimeters wide and 15.5 centimeters long, sized to fit standard commercial lasagna pans and retail packaging dimensions. After cutting, the pieces are lifted by electrostatic air knives that use controlled static charges to separate and align them without physical contact. They are then conveyed over a vibrating platform that gently shakes off residual semolina dust, which is collected and recycled into animal feed. The sheets pass through an ultraviolet sterilization chamber that eliminates surface microbes without altering taste, texture, or nutritional value. Each sheet is individually inspected by a machine vision system that scans for color consistency, surface texture, and the presence of any embedded foreign particles. Defective pieces are ejected into a waste bin using compressed air jets, while acceptable sheets continue to the packaging line. Packaging occurs in a sterile environment where each lasagna sheet is placed into a pre-formed, food-grade cellulose tray lined with a moisture barrier film. The trays are sealed under vacuum with a heat seal lid that creates an airtight barrier, extending shelf life to 18 months without preservatives. Inside each sealed tray, a small silica gel packet is inserted to absorb any residual moisture that might develop during transit or storage. Before sealing, each tray is passed through an X-ray scanner that detects metallic contaminants, plastic fragments, or glass particles invisible to the naked eye. Every package is labeled with a unique QR code linked to its production batch, ingredient source, and quality assurance logs accessible via manufacturer portals. The sealed trays are stacked by robotic arms onto pallets wrapped in heat shrink film, then moved by autonomous guided vehicles to climate-controlled storage. Storage rooms maintain a constant 16 degrees Celsius and 45% relative humidity to prevent brittleness or microbial growth over extended periods. Random samples are pulled daily and sent to the in-house lab for cooking tests, where technicians measure rehydration time, firmness after boiling, and sauce absorption rate. The target is for each sheet to absorb exactly 45 milliliters of water in 8 minutes of boiling, achieving a texture that remains firm yet pliable under cheese and sauce. Lasagna sheets are never pre-cooked. Their dry state is intentional, allowing consumers to layer them directly into casseroles without blanching. The entire production line runs continuously, processing over 800,000 sheets per hour, with each machine synchronized to within 0.01 seconds of the next. Maintenance is performed during scheduled 15-minute windows every 4 hours, during which steam jets clean every surface the dough contacts. No lubricants are used on any part of the machinery that touches the dough. Instead, food-grade silicone coatings are applied to rollers to prevent sticking. All personnel entering the production area must pass through an airlock chamber that blows away particulates before entry, and gloves are changed every 30 minutes. The factory's ventilation system filters air 22 times per hour, maintaining a particulate count lower than that of a hospital operating room. Every batch of semolina is tested for protein content before use, with only flour yielding 12.5 to 13.2% gluten accepted for lasagna production. The water used is reverse osmosis, purified and mineral balanced to ensure consistent dough behavior across different regional water sources. Wastewater from cleaning is treated with activated carbon and UV sterilization before being reused for non-food contact purposes like floor washing. Unused semolina dust is sold to organic fertilizer producers, and packaging film scraps are recycled into industrial plastic pellets. Energy recovery systems capture heat from the drying tunnels and redirect it to pre-warm incoming water, reducing overall energy consumption by 37%. AI algorithms analyze vibration patterns in the rollers and predict bearing failures up to 72 hours in advance, eliminating unscheduled downtime. Each lasagna sheet is designed to expand by no more than 3% when cooked, ensuring layers remain flat and evenly distributed in the finished dish. No additives, preservatives, or enzymes are used. Only semolina, water, and time. The final product contains zero cholesterol, no trans fats, and less than 0.1% sodium, making it suitable for dietary restrictions worldwide. Each sheet is identical in weight, thickness, and cooking behavior to every other sheet produced in the last 10,000 batches. The factory produces enough lasagna sheets annually to assemble over 50 million individual lasagna dishes, each one ready to be layered, baked, and served. Once packaged, the trays are loaded onto refrigerated trailers that maintain a steady 8 to 12 degrees Celsius during transit across continents. Noodle production in factories begins with the careful selection of high-protein wheat flour, often blended with egg solids or alkaline salts, depending on the regional style being manufactured. Unlike pasta, many noodle varieties require the addition of kansui, a mineral solution of potassium and sodium carbonate, to achieve their characteristic yellow hue and springy texture. The flour and liquid ingredients are mixed in a vertical spiral mixer that gently folds the dough rather than kneading it aggressively, preserving delicate gluten networks. The mixing process lasts only 10 to 12 minutes, as prolonged agitation would overdevelop gluten and make the noodles too chewy or tough. Once combined, the dough is immediately transferred to a resting chamber where it sits under a weighted lid for 20 to 30 minutes, allowing hydration to complete and proteins to relax. This resting phase is non-negotiable. It enables the starch granules to swell fully, ensuring even cooking and preventing mushiness later in the process. After resting, the dough is passed through a series of precision rollers that flatten it into a continuous ribbon, each set reducing thickness by just 0.05 millimeters to avoid tearing. The final ribbon is typically 1.2 millimeters thick, but this varies slightly depending on whether the noodles are intended for ramen, udon, or instant cup varieties. As the ribbon exits the rollers, it is lightly dusted with rice flour or cornstarch to prevent sticking, avoiding wheat-based flours that could alter flavor or cooking behavior. The sheet then moves onto a perforated conveyor belt, suspended above a low-temperature drying zone that begins moisture removal without hardening the surface. Producing 10 million Snickers bars begins with raw ingredients delivered in industrial-scale volumes. Liquid glucose, granulated sugar, skimmed milk powder, cocoa liquor, cocoa butter, vegetable fats, peanuts, egg white, lactose, and emulsifiers. All materials are stored in temperature-controlled silos, tanks, or hoppers, connected by stainless steel pipelines and pneumatic conveyors to feed the production lines with uninterrupted flow. The first step is the nougat base. A pre-blend of sugar, glucose syrup, and water is piped into a continuous cooker. This cooker operates under controlled heat and vacuum, rapidly boiling the mixture to reach the target solid's content while minimizing color and flavor degradation. The hot syrup exits at around 120 degrees Celsius and is sent straight into a high-speed whipping chamber. Inside the whipper, dried egg white and milk powders are injected. A rotor-stator system beats the mix at high speed, incorporating air into the matrix to create the nougat's aerated structure. The density is tightly regulated with inline sensors measuring viscosity and expansion ratio in real time. Once aerated, the warm nougat mass flows through heated stainless steel pipes and is deposited as a continuous sheet onto a wide belt coated with a release film. As the sheet advances, calibrated rollers compress it to a uniform height, typically between 12 and 15 millimeters. The sheet then passes through a cooling tunnel that drops its internal temperature below 20 degrees, stabilizing the structure for the next layer. Once cooled, the caramel layer is applied. Caramel production occurs in a separate closed-loop cooker, where a mixture of glucose syrup, sugar, dairy fats, and milk solids is cooked under vacuum to reach the desired viscosity and chew. The caramel exits the cooker at around 118 degrees and flows into a depositing manifold. This manifold lays a smooth, uniform layer of hot caramel directly onto the nougat sheet. While the caramel remains soft, whole roasted peanuts are added. Peanuts, sourced in bulk, are first passed through an inline sifter to remove debris, then lightly roasted in continuous rotary ovens. After roasting, they are cooled and metered onto the caramel layer using a vibratory conveyor with adjustable baffles. The conveyor distributes peanuts evenly across the moving sheet, ensuring every section contains a balanced nut density. The peanut caramel nougat tri-layer now proceeds through a final compression roller, bringing it to the finished bar thickness. From here, the slab enters a chilling tunnel that gradually reduces its temperature from ambient to below 10 degrees Celsius over a span of 20 meters. This ensures the caramel sets just enough to be cleanly cut without oozing or deformation. After chilling, the slab moves to a guillotine cutter. First, rotary blades cut it lengthwise into continuous ribbons, each the width of a Snickers bar. Then, a high-speed guillotine slices each ribbon into uniform bar-sized segments using servo-controlled motion synchronized with the belt speed. Blades are coated with a non-stick surface and cleaned automatically to prevent buildup. Each freshly cut bar now enters the enrobing stage. Bars are transferred onto a wire mesh conveyor belt and passed beneath a curtain of tempered milk chocolate. This chocolate is continuously circulated through a 3-stage tempering system, where it is heated, cooled, and reheated to create stable cocoa butter crystals. The chocolate is maintained at 30 to 37 degrees Celsius, ensuring proper viscosity and flow. As each bar passes through the enrober, it is coated on all sides, top, bottom, and flanks. The base of the bar receives a bottoming layer of chocolate from a pre-flooded section of the belt. Excess chocolate is removed by an adjustable air knife that blows a focused jet across the bar's surface, shaping the characteristic swirl patterns on top. A vibrating section under the mesh belt removes bubbles and smooths the surface. The enrobed bars enter a cooling tunnel that spans 30 meters and consists of multiple zones. Each zone gradually reduces the air temperature, allowing the chocolate to crystallize evenly. The final zone chills the bars to below 8 degrees Celsius, locking the coating into a firm, glossy finish with the correct snap and bloom resistance. After exiting the tunnel, each bar is inspected by a vision system. High-resolution cameras scan every unit for shape, surface quality, alignment, and chocolate coverage. Defective bars, those with missing peanuts, air gaps, or surface defects, are automatically rejected through pneumatic diverters. Accepted bars move on to the wrapping section. Each bar is fed into a flow wrapping machine running at speeds of up to 100-200 bars per minute. Wrapping film, pre-printed with branding and batch codes, is drawn from a roll and cut to size by rotary knives. As each bar passes through, it is wrapped in film, heat-sealed along the underside, and crimp-sealed at both ends. The sealing jaws operate with synchronized thermal and pressure settings to create tight, tamper-proof packages. Wrapped bars are conveyed through a metal detector calibrated to detect both ferrous and non-ferrous contaminants. Any bar triggering the system is rejected. Compliant bars continue to the check weigher, which confirms unit weight to within plus and 1.5 grams. Any deviation results in immediate removal from the line. The verified bars are then grouped and collated. Robotic arms pick up sets of bars, typically 24, 36, or 48, and place them into cartons automatically erected from flat blanks. Hot melt glue is applied by precision nozzles to secure the flaps. Cartons are closed, sealed, and printed with best before dates using high-speed inkjet coders. Cartons then advance to the palletizing station. Here, robotic palletizers arrange the cartons into stacks on standard Euro or GMA pallets, using a pre-programmed pattern that alternates layer direction for stability. Slip sheets are inserted automatically between layers. Once a pallet is complete, it is wrapped with stretch film by a rotating arm that applies the film under tension to create a rigid, transport-stable unit. Throughout the entire process, programmable logic controllers coordinate equipment motion, timing, and feedback across the line. Each machine is connected to a centralized SCADA system that logs production metrics, sensor values, fault codes, and output counts in real time. Operators monitor touchscreen panels displaying temperature trends, motor speeds, belt loads, fill levels, and inspection alerts. The chocolate tempering unit is governed by 3 separate thermal zones, each independently controlled by thermocouples and heating elements. Syrup bricks is measured inline using optical refractometers. Nougat density is monitored by in-pipe density meters. Caramel viscosity is controlled by adjusting vacuum level and cook temperature. Every variable is closed-loop controlled, meaning it adjusts itself based on sensor readings. Carbon dioxide is used in modified atmosphere packaging for bulk storage formats. The gas is injected into large multi-bar containers to displace oxygen, extending shelf life. These containers are flushed, sealed, and stored in chilled holding bays before being distributed. Clean-in-place systems automate sanitation. Heated caustic detergent, flows through all nougat, caramel, and chocolate handling systems at the end of each run. Pipes, tanks, depositors, and pumps are cleaned in sequence, followed by hot water and sanitizing rinse. Each cycle is logged with flow rate, contact time, and temperature. To produce 10 million Snickers bars, the line operates continuously for multiple days across several parallel lines. A single high-speed line can produce up to 1,100 bars per minute. With 10 such lines running in tandem, nearly 720,000 bars are produced per hour. In under 14 hours, 10 million bars are complete. Each bar is mechanically identical. Same mass, same shape, same structure. From aerated nougat to sticky caramel, crunchy peanuts, and smooth milk chocolate coating, the process controls every variable. Flow meters, torque sensors, load cells, vision cameras, pH probes, temperature controls, and synchronized motors maintain the consistency required for mass production. Every action is automated, but none is simple. The caramel must flow, but not run. The nougat must hold its structure without hardening. Peanuts must fall in even distribution without clumping or rolling. Chocolate must be tempered, coated, shaped, and solidified, without bloom, swirl misalignment, or trapped air. Producing 10 million Reese's peanut butter cups begins with the bulk delivery of core ingredients: roasted peanuts, cocoa liquor, cocoa butter, sugar, salt, milk solids, dextrose, emulsifiers, and stabilizers. Raw materials arrive in tankers, super sacks, and silo containers, and are fed into the production system via automated pneumatic transfers, conveyor augers, or liquid pumps, all connected to centralized control systems that regulate flow, temperature, and mass. The peanut butter core is produced first. Whole roasted peanuts are delivered directly into an industrial-size vibrating hopper. The hopper separates debris, splits, and undersized fragments through a combination of screen grating and air jets. The selected peanuts are passed through a second roasting stage in a continuous rotary drum oven, bringing their internal temperature above 160 degrees C. This ensures uniform oil release and deepens flavor. As they exit the roaster, the peanuts are immediately cooled using a forced air cyclone system to prevent over-roasting. Cooled peanuts are fed into a hammer mill, where rotating steel blades grind them into a fine, warm paste. The paste flows directly into a ribbon blender, where sugar, salt, dextrose, and stabilizers are added. The blender's high shear paddles fold and mix the ingredients, creating a thick, creamy filling with a controlled moisture content and spreadable viscosity. Viscosity sensors and torque meters monitor the blend in real time. The finished peanut butter is pumped into heated jacketed holding tanks equipped with agitators that keep the filling homogeneous and at a stable flow temperature around 45 degrees Celsius. Meanwhile, chocolate production runs in parallel. Cocoa liquor, cocoa butter, sugar, milk solids, and lecithin are fed into a high-capacity conche. The conche kneads and heats the mixture, allowing moisture and acidity to evaporate. Internal temperature is held between 50 °C and 60 °C. Once the flavor has developed and the texture has been refined to a smooth mass, the mixture is transferred to a 5-roll refiner. In the refiner, steel rollers shear the chocolate mass to reduce particle size to below 20 microns. The refined chocolate is then conched again to polish the particle surfaces, improve flow, and enhance melt. From the conche, the liquid chocolate is pumped through heat-maintained stainless lines into tempering units. Tempering machines cycle the chocolate through 3 thermal zones: heating to fully melt all crystals, cooling to encourage stable seed crystal formation, and reheating to melt unstable forms. The result is chocolate with stable beta crystals that produce a glossy finish and crisp snap. Now the forming line is activated. Preformed paper cups are dispensed from a magazine feed into indexed molds on a conveyor belt. A depositor head descends over each cup and fills the base with a measured dose of tempered chocolate. This forms the bottom, shell. As the chocolate hits the cup, the molds are vibrated rapidly, forcing the liquid to spread evenly and coat the cup base. The conveyor then carries the partially filled cups through a cooling tunnel that drops the chocolate temperature to around 10 degrees Celsius over several minutes, solidifying the shell and contracting it slightly away from the paper wall. Next, the peanut butter filling is applied. A piston depositor aligned with the mold indexing system dispenses a precise slug of peanut butter directly onto the cooled chocolate base. The volume is tightly controlled, typically 10 to 15 grams per cup, depending on size variant. The warm filling spreads slightly on contact, but retains its form due to its balanced fat structure and cooling effect from the base. A brief second cooling tunnel pass stabilizes the core enough to support the top chocolate layer. The top layer of chocolate is deposited last. Another depositor head applies a final pour of tempered chocolate over the peanut butter core. Vibration removes any trapped air and flattens the surface to an even plane. This final deposit seals the core entirely, forming the completed cup. The filled cups now pass through the primary cooling tunnel, a multi-zone chamber that gradually drops the internal temperature of each cup to ensure uniform crystallization. Airflow, humidity, and conveyor speed are precisely tuned. The full cooling cycle lasts around 10 minutes, allowing the chocolate to fully solidify without forming sugar bloom or fat migration marks. As the cups exit the tunnel, they undergo automated inspection. Vision systems scan every unit for fill height, surface uniformity, and alignment within the paper cup. Cups with off-center deposits, cracked surfaces, or exposed peanut butter are automatically rejected by robotic arms or pneumatic gates. Approved cups continue to the wrapping station. A pick-and-place system lifts each cup and transfers it to the wrapping infeed. Wrapping film, pre-printed with branding and registration marks, is cut to size and wrapped tightly around each cup using a twist wrapping mechanism. The ends are pinched and twisted shut by synchronized spinning belts. Wrapping speeds can exceed 1,000 units per minute per line. Wrapped cups are conveyed through a metal detector calibrated for high sensitivity to both ferrous and non-ferrous contaminants. Any package triggering an alert is automatically diverted. Cleared products are grouped into collating lanes. Collators arrange cups into blister trays or multi-packs. A robotic grouping arm aligns sets of cups and loads them into thermoform trays or folding cartons. These cartons are pre-formed in a high-speed erector. Hot melt adhesive is applied to flaps, and cartons are sealed using servo-driven compression plates. Cartons are printed with date codes and batch numbers using thermal inkjet or laser coders. Completed cartons move toward the palletizing area. Robotic palletizers lift cartons using vacuum, grippers or adjustable forks, and stack them onto wooden or plastic pallets in a fixed interlocking pattern. Slip sheets may be added between layers. Each full pallet is conveyed to a stretch wrapper. A rotating arm applies film from bottom to top, binding the load securely for transportation. All stages are governed by programmable logic controllers. Each machine communicates via industrial Ethernet to a centralized control room. SCADA interfaces display real-time production data, including belt speeds, depositor accuracy, wrapping count, rejection rates, temperature profiles, and chocolate viscosity. Ingredient dosing is closed-loop controlled. If sugar concentration drifts in the peanut butter mix, the feeder corrects flow automatically. Chocolate viscosity is monitored using inline rotational viscometers. Fill weights are verified by high-speed load cells. Position sensors and servo motors keep all timing synchronized across multiple parallel lines. Each line is designed for continuous operation. Changeovers are handled with toolless part swaps and automated cleaning sequences. Clean-in-place systems, wash tanks, pipes, and depositors between shifts. Heated caustic detergent is pumped through all product contact lines, followed by a water rinse and final sanitizing flush. Flow rate, contact time, and return temperature are logged and verified automatically. Producing 10 million peanut butter cups requires multiple synchronized lines running at high throughput. A single high-speed line can produce over 1,200 units per minute. 10 such lines operating in parallel generate 720,000 units per hour. In a continuous run, lasting just under 14 hours, the full batch of 10 million is completed. Each cup is mechanically identical. Same chocolate mass, same peanut butter volume, same shell thickness, same twist wrap tightness. The consistency is achieved through calibrated depositor nozzles, servo-actuated plungers, precision-heated tanks, and closed-loop feedback across every stage of production. Key tolerances are maintained. Chocolate fill weight within plus as 0.5 grams, peanut butter center within plus 1 millimeter of alignment, wrap tension within 2%, seal temperature within plus 1.5 degrees Celsius. Rejects are tracked and analyzed automatically to detect trends before they cause system-wide variation. Temperature is crucial. Chocolate crystallization, peanut butter viscosity, cooling tunnel performance. Every step is sensitive to thermal drift. Thermocouples monitor all zones, from tanks to tunnels. If any zone deviates from range, alarms sound and the affected section is automatically adjusted or stopped. From the peanut grinding to the pallet wrap, the process is fully integrated. There are no idle steps. Syrup mixing, shell forming, core deposition, sealing, cooling, inspection, wrapping, cartoning, and palletizing flow in continuous sequence. There is no manual intervention. Everything moves in rhythm, guided by sensors, actuators, and control algorithms. Producing 10 million M&Ms begins at the granule level. Core ingredients like sugar, cocoa mass, cocoa butter, milk solids, corn syrup, and food-grade colorants are delivered in bulk. Each component is unloaded into stainless steel silos, insulated storage tanks, or vacuum-sealed hoppers. From there, pneumatic conveyors and positive displacement pumps transfer the raw materials into the processing line with exact flow control. Every ingredient is monitored by mass flow meters, auger dosing systems, and load cell integrated vessels to ensure accurate, repeatable input ratios. The first major step is creating the chocolate centers. These are not flat discs to start with. They begin as lentil-shaped chocolate pieces, formed, cooled, and prepared for shell coating. Chocolate production occurs in a multi-step blending and refining system. Liquid cocoa liquor, cocoa butter, and sugar are pumped into a conche. In this high shear mixing chamber, ingredients are heated and agitated over hours, reducing acidity and moisture while developing flavor. The mass then flows into a 5-roll refiner. This machine crushes the chocolate through narrowing steel rollers until particle size falls below 20 microns, producing the creamy texture needed for M&M's centers. The refined chocolate returns to a second stage conche for additional smoothing. From the conche, the chocolate mass is pumped through jacketed pipes into tempering units. These systems rapidly cycle the chocolate through heating, cooling, and controlled reheating phases, encouraging the formation of stable cocoa butter crystals. Tempered chocolate exits at a tightly maintained viscosity and temperature, ready for molding. The molding system produces the core. Individual chocolate lentils are formed by depositing droplets of tempered chocolate onto a chilled belt. As each droplet lands, it spreads slightly before solidifying into the iconic disc shape. High-speed vibratory tables level and settle each piece before the belt enters a rapid cooling tunnel. Cold air circulates above and below to ensure uniform hardening. Each M&M-sized piece is checked by laser sensors for thickness and diameter tolerance. Once solidified, the chocolate cores are collected into stainless steel bins and conveyed to the panning room. Here begins the defining process: sugar shell coating through precision, layering in automated panning drums. The panning drums are large rotating cylinders with polished stainless interiors. Thousands of chocolate cores are loaded into each drum. As the drums rotate, a fine mist of sugar syrup is sprayed through atomizing nozzles. The syrup is a concentrated mix of sugar, glucose, and water, heated to remain fluid but not overly thin. The chocolate cores tumble while the syrup coats them evenly. Cold, dehumidified air is blown into the drum chamber to dry each layer. This process is repeated across dozens of cycles. Each round adds a thin sugar layer. The rotation angle, drum speed, airflow, syrup volume, and spray pattern are all programmable and adjusted in real time by feedback systems. The cores grow gradually, layer upon layer, until the shell thickness reaches the target range. Throughout the panning process, non-contact sensors monitor shell diameter growth. Cameras detect shape anomalies or cracks. Any defective units are removed automatically using vibration sorters and size classifiers. After achieving the proper shell thickness, the final stage of the sugar coating is the polishing sequence. Polishing begins with a thin application of carnauba wax and food-grade glaze. These are sprayed inside the rotating drum, creating a slick coating on the sugar shells. Buffing arms inside the drum press and polish the surface as it spins, producing the high-gloss finish M&Ms are known for. The shine is not just cosmetic, it also protects the candy shell from humidity and reduces friction during packaging. Now, the finished M&Ms are conveyed into the color coding system. The distinctive red, yellow, blue, green, orange, and brown shells are not coated one at a time. Instead, batches are divided and each drum is designated for a specific color. Colorant solutions, made from water-soluble dyes and a sugar base, are sprayed into the rotating drum in much the same way as the shell syrup, but in smaller quantities. The dyed layers are dried with a gentler airflow to prevent streaking or pooling. After color coding, another pass of polishing glaze is applied for clarity and shine. After drying, M&Ms are released onto vibrating conveyor belts. These belts sort the pieces, prevent sticking, and align them into single-file lanes for printing. A laser-guided inkjet system prints the signature M on each piece. Optical sensors locate the center of each candy and trigger the inkjet nozzle to fire the white food-grade ink at exactly the right spot. The print dries in under 1 second using forced air and low heat. The print tolerance is within 1 millimeter per piece. Any candy without a printed M or with a misprint is identified by high-resolution cameras and removed from the stream. Printed M&Ms pass through a metal detector that scans for ferrous, non-ferrous, and stainless steel contaminants. They then flow into a check weigher, which confirms the average weight of grouped candies matches the package specification. If the weight falls outside a narrow band, that group is rejected. Now the candies are funneled into packaging units. Depending on the format, single-serve pouches, theatre boxes, tubes, or multi-packs, the M&Ms are guided through volumetric fillers, counting systems, or load cell-based dosing mechanisms. For pouches, horizontal form-fill-seal machines draw roll-fed plastic film, print batch codes, and form it into bags. A vertical chute dispenses a fixed volume of M&Ms into each bag, which is then sealed with a heated jaw. For boxed formats, cartons are formed from flat blanks by a mechanical erecting arm. Pre-grouped M&Ms are poured into the boxes using funnel-shaped hoppers with vibratory feeders to ensure consistent flow. Boxes are sealed using hot melt glue and compressed under pressure for final closure. All packages are marked with laser-etched batch codes and expiration dates as they exit the system. Finished packages move on to conveyor belts toward the robotic palletizing area. Here, industrial robots equipped with vacuum pads pick up multiple units at once and stack them in program formations onto wooden pallets. Slip sheets are inserted automatically for stability. Once stacked, the pallet moves to a stretch wrapping unit. A rotating arm applies plastic film tightly around the load to prepare it for distribution. To reach 10 million units, the process relies on multiple parallel lines. Each high-capacity line can produce more than 2,000 pieces per second. With 10 synchronized lines running continuously, the factory generates 72,000 pieces per second, over 4.3 million per minute. In just under 40 minutes, the full 10 million pieces are completed, each one identical in size, shape, coating, gloss, and print. All steps are governed by programmable logic controllers. The entire factory is coordinated through a distributed control system, with real-time SCADA dashboards showing every variable: syrup viscosity, shell thickness, air humidity, shell growth rate, rotation speed, dye concentration, gloss level, printing accuracy, and package weight. Sensors monitor the production line at every point. Shelling drums use load cells to detect overfill. Thermocouples track temperature inside conchis, tanks, and coating units. Flow meters control syrup delivery. Cameras confirm print legibility. Servo motors handle belt timing, robotic arm movement, and package alignment. Cleaning cycles run automatically between batches. Sugar lines, chocolate tanks, conchis, panning drums, and depositor heads are cleaned using hot, circulating detergent, followed by high-pressure rinses. All cleaning steps are validated by chemical conductivity sensors and logged for traceability. The factory layout is linear but modular. Chocolate production, shell coating, coloring, printing, and packaging are linked by buffer zones that allow for surge capacity. If one stage slows, others continue without shutdown. Every section has redundant machinery to allow for changeovers and maintenance. Tolerance ranges are tight. Shell thickness must fall within +0.15 mm. Chocolate center weight must remain within +0.2 grams. Printing alignment cannot vary more than 1 mm. Shell color concentration is monitored by spectrophotometers to ensure consistency across millions of pieces. Every variable, from syrup crystallization to drum angle to print timing, is calibrated for absolute uniformity. This level of precision ensures that 10 million M&Ms are not just mass-produced, but identically produced. Each one carries the same shine, the same crunch, the same chocolate-to-shell ratio, and the same instantly recognizable M. From grinding cocoa to molding chocolate, from layering sugar to polishing glaze, from color batching to robotic stacking, the process never stops. The result is a continuous stream of motion, heat, rotation, and control, where every piece, every shell, and every package flows through the system in perfect mechanical choreography. It begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5-to-1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens, and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces, syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drinks base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision.